Good morning, everybody. We've been talking a lot about motion and velocity and displacement and acceleration. We've been plugging those values into formula. We've been coming up with answers. We've looked at units and dimensions. But one of the things that's important in learning is that be able to visualize the concepts. And one of the ways to do that is to look at how these concepts interact on a graph. So we're going to look at graphing motion today, and you can see by the title that this is what we're planning to do. And thought you might want to take a look at that. So let's go to the first slide. What I'm giving you here are 3 slides, 3 graphs, 3 lines, 3 curves of displacement versus time. Now, if you look at graph number 1, where the pen is here, you can see that the vertical axis, the y-axis, measures displacement, and the x-axis measures time. And let's talk a little bit about what this means. If you look at this object, this is the graph of of an object in motion. Tell me what you know about this object. Turn off the recording and think a moment about what is this graph telling you. So if you said that this is telling me that this is an object that's not moving, you're correct. In the second graph, take a look, give it some thought. I'll be right back. So if you determine that the object was indeed moving and that its displacement was changing at the same rate over time, hence a straight line, you're correct. So if down here at the bottom I've written something that I think will be helpful with these 3 graphs, that the slope of a displacement versus time curve or line is the velocity. So if I take the slope of this line, what do I get? 0, correct? So the displacement here is 0. The velocity here is 0. If it's not moving, it's not going anywhere. And here, if I take the slope of this line, displacement over time, and remember slope is delta y over delta x. In this case, it's the change in displacement over the change in time. So the slope is going to give us change in displacement, change over time, which we know to be velocity. So here, the slope never changes. That tells us that the velocity never changes. So this is a graph of constant velocity or speed. What do you think is going on here? By the way, this is supposed to be a parabolic, half a parabola, straight line. Straight curve. My hand got a little wobbly on there, so excuse the wobbliness. So the first 10 is, what do we know about the slope of this curve? And we can see that along each point, the slope is getting steeper and steeper and steeper. Well, if the change in displacement over the change in time is increasing and increasing and increasing, so is the velocity, because slope of a d versus t curve is velocity. So in this curve, velocity is changing regularly, because the slope, if this were a smooth line like it's supposed to be, the slope would be increasing at a regular rate. So what do we have there? What do you know about changing velocity? It's called acceleration. So the only one of these graphs where acceleration is occurring is this third graph here. Let's look at number 3. Trying to look at number 3. Okay. Velocity versus time. And you'll notice that it's the same 3 curves with the same wobbly third curve that's supposed to be straight parabolic line, straight curve. Not straight, but straight lines anyway. Smooth lines, I guess is what I want to say. And what do I know about this object right here? Well, think about it for a minute and tell me how you would describe the motion of this object. Okay, if you said that the motion, the velocity was unchanging, you're correct. Is this velocity, is this car, is this object at rest? No. It's got a constant speed. It's moving at a constant velocity. So let's take a look over here and we see what's happening. The velocity changes at a regular pace over time. And let's go back down again. The slope of a velocity versus time line or curve is the acceleration. And if you remember what slope is delta y over delta x, change in velocity over change in time, and that's been our definition of acceleration. So the slope of a velocity versus time line or curve is acceleration. Delta v over delta t, or delta y over delta t. Slope, velocity, acceleration, the same. So in this situation, slope is 0, acceleration is 0. It's not accelerating, moving at a constant speed. What do you think's happening here? So you have a constant slope, and the slope of a velocity versus time curve is acceleration. So this means that the acceleration is uniform. It doesn't change. So if the slope of this were 2, that would tell us the velocity is changing by 2 meters per second each second. It starts at 0, it goes to 2 meters per second after 1 second, it's 4 meters per second after the next second, it's 6 meters per second, etc. So constant slope means a constant delta v over delta t. The velocity is changing at the same rate. As time increases, velocity increases. So this is accelerating, and it's accelerating at a constant or uniform rate. Now back over here, if the slope of a v versus t line or curve is acceleration, and the slope is changing constantly, in fact it's getting steeper and more steep, that's telling us that the acceleration is changing constantly. In this course, we're not going to deal with constantly changing acceleration, but I wanted you to see it on the graph and kind of start thinking about what that might mean. We will deal with uniform acceleration, and we've already talked about falling objects, and their uniform acceleration is 9.8 meters per second each second. So the slope of that curve would be 9.8. Think about if you have any questions, and we'll come back to those questions shortly. If we look at area under the curve, so for example, one of the things we can do is, if I highlight this right here, and if I look at this area right there, all this area under this curve, that's nasty looking, isn't it? How am I going to find that area without using calculus? Well, basically, it's a rectangle. And so you find the area of a rectangle using base times height, y times x, velocity times time. And what do you get when you multiply velocity times time, you get displacement. So if this were the 3-second mark, and this were the 10 meters per second mark, 10 times 3 is 30. After 3 seconds, this thing would have moved 30 meters. Now, if I want to do the area under this curve, remember your formula for the area of a triangle. I take the base times the height, and it's 1/2 of that, so 1/2 BH. And whatever I get for the area here, that's going to tell me how far the object has gone from its starting point at this time. And lastly, let's take a look at acceleration. Let me see if I can find it. Here we go. Think a little bit about what that first graph is telling us. If your answer is that the acceleration is constant, you're correct. So it is accelerating. The acceleration is not changing. It's very similar to free fall. It is like free fall. It's unchanging or uniform acceleration. Here we have acceleration that's changing in a regular way over time. And once again, this is not going to be something we cover in this course. And here we know that this acceleration is changing at an exponential rate. We won't be covering that either. We will look at uniform acceleration. Now, if you take the area under an A versus T curve, once again, base times height is going to give us the area, or acceleration times time. And when we multiply acceleration times time, we get velocity. So I can say, if this were the 3.3 second mark, I could say at 3 seconds, this object was traveling however many meters per second you come up with when you multiply 3 times this. So whatever the area is also tells us what the velocity is. Same thing here for area under the curve. So if we were to sum this all up, and we look at all 3 situations here, tell me if you can see a pattern in the 3 lines, A, B, C, D, E, F, G, H. Anything you can see that's similar on each 3 lines? So if you said that acceleration is changing uniformly there, and uniformly there, you're correct. These 3 are saying the same thing. F, E, and C. They all represent uniform acceleration. The slope of a D versus T curve is velocity, and this velocity is constantly changing. That's acceleration. If the slope of a V versus T curve is acceleration, and the slope is constant, you've got constant acceleration. Just like you had a constant changing velocity here, you've got a constant velocity here, and you have here a constant acceleration. So both of these represent this, all 3, uniform acceleration, uniform acceleration, uniform acceleration. I know there'll probably be some questions about that later. So that's the first pass that we're going to take at looking at motion on graphs, and we'll continue.